All right, I want to do a quick example of how we would analyze a function using the second and first derivative. So let's start with the fact that we are given a first derivative. We are given the various rates of change, and it works out to be 4x cubed minus 12x squared. So first thing we need to do is say, well, when is that derivative equal to 0? And a little bit of algebra tells us that when x equals 0 and when x equals 3, the first derivative will be equal to 0. Those are the only critical points. We have does not exist because this is differentiable throughout its domain. So the second thing we know we're going to need is the second derivative. So we'll do a quick second derivative. And we see that that is 12x squared minus 24x. Figuring out when the second derivative is equal to 0, we find that that's at x equals 0 and x equals 2. So what I want to do is I want to build this chart, and this chart is going to be a very good way to keep track of these types of problems. I recommend that you do this every time. And the three things that we will have on our chart that we are analyzing is the original function, the first derivative, and the second derivative. So we know that the first derivative is 0 here and here. And a little bit of analysis, and by analysis I mean plug in some numbers. We know that this is less than 0 here, it is less than 0 here, and it is greater than 0 there. So function is going down, and then it stops going down, and it goes down again, and then it stops going down, and then it goes back up. So right off the bat, we know that we are going to have a minimum right there. And since it was coming down over here, and since it was then turned and goes back up again, this has to be an absolute minimum. So let's look at the second derivative. The second derivative, we see that it is equal to 0 here, and it is equal to 0 here. And a little bit of quick analysis tells us that it is positive here, it is negative here, and it is positive over here. And so I now know that since it is switching from concave down to concave up right here, that this must be an inflection point. We can confirm our minimum by noticing that the second derivative is positive, which means concave up. And we can confirm that we have, well, not confirm, but also tell that we must have an inflection point here. We know that something happened going down, pausing, and then going down again, and the concavity changes, so boom, another inflection point. So looking at this, what we basically then see is that our graph must look like this. It goes down, it flattens out and changes concavity, and then it goes down and it flattens out, doesn't flatten out. We have a derivative of 0 here. We do not have a derivative of 0 here. I'm going to run out of room here, but changes concavity, reaches a minimum, and then goes back up again. So we have an inflection point right here. We have an inflection point, and sorry about the scale, an inflection point here. We have a minimum right here, and we see that it must be an absolute minimum. And we notice that we have no absolute maximum based on the fact that it goes up in both directions forever. So what are the things that we need to watch for? What are the things that we're interested in? I will highlight them in gold. First of all, critical points. Those have to be either a minimum or a maximum or an inflection point. Using the second derivative test, we can tell that concave up gives me a critical point as a minimum, and that changing concavity gives me an inflection point. And then we can determine absolute minimum based on the behavior of the graph everywhere else, and absolute maximum based on the behavior of the graph everywhere else. All right. What are the takeaways? The things that are highlighted: critical points, inflection points, concavity, and building this chart, which will allow you to see all of the important points and what is happening at each of them. All right. Thanks for watching. Hope you learned something.